So today our lesson is on U substitution, and we finally get to see the brilliance of Leibniz's notation and the way that he's able to use his dy by dx as a fraction and break it into pieces. So this method is primarily used when you're dealing with some type of function which appears in whatever way to be derived from a chain rule. And you know you want to go backwards in the chain rule, but it might prove to be a little bit too complex. We saw an example of this the other day. We anticipated that the antiderivative of the sine of 5x would be equal to a negative 1/5 cos of 5x. And we did that because we said, well, if we took the derivative of a 5x, there should be a 5 there. So we just kind of guessed that the 1/5 should show up. So now we're going to take a look at how to do this using U substitution. The first thing that we do is we choose to take a look at what function is it that we want to replace with the letter U. This is usually something which is a function within a function. So in this case, U is going to become 5x. Using Leibniz notation, we will take the derivative of it, and then we will rearrange it by multiplying the dx from the left up to the right and dividing the 5 down over to the left-hand side as a 1/5. We then rewrite the integration with a u, and we replace the dx with a 1/5 du, which comes down here from the bottom of the screen. We then take the antiderivative of the sine of u, which is a negative cos u, and we tidy it up. Negative 1/5 cos u plus c. Let's look at another example. We're going to take a look at the integral of x times the sine of x squared dx, which initially looks like a product rule. But if you look at it carefully, you'll notice that, hey, that x squared function, if I took the derivative of it, I would get an x. It's actually a 2x, but the x is there. So if I let the u equal x squared, take the derivative of it, and rearrange, I can end up with 1/2 du is equal to x times dx, and then rewrite my integral. So this then becomes the integral of the sine of, I replace my x squared with my u, and I replace my x and dx with a 1/2 du. I wrote that incorrectly on the screen. It should be a du. I take the antiderivative, tidy it up, and now I plug the x squared back in to my original. So let's look at some steps. Number one, we need to choose that function that's going to become our u. Look for something that a chain rule might produce another piece of the function that's already visible to us. We're going to write the u down with our let statement, and we'll take the derivative using Leibniz's notation. We're going to rearrange the du by dx statement using basic algebra to get the dx and whatever else that we might have already seen in the integration on one side, so that we'll be able to replace it in a later step. And then finally, we're going to integrate with respect to the letter u and replace at the very, very end our original function back in. So just a nice few series of steps to be able to follow to figure these out. Let's look at another example. Here we've got the integral of x over top of the square root of 1 minus 4x squared dx, the derivative of a 4x squared could be an x. So that's why we'll let u equal 1 minus 4x squared. Take the derivative, rearrange, and then replace all the pieces as we are seeing them. The u goes on the bottom. The x dx gets replaced with the negative 1/8 du. The 1 over square root of u is rewritten as a u to the power of a negative 1/2. We rearrange and do the antiderivative, and we're able to come up with our solution. So that's the basics of u substitution. You may wish to rewatch this video one more time before you actually go and take a look at my next video. My next video, I have a few more examples, and then I have a short homework assignment for you to work on. Thank you.